Welcome to the deep dive.
Hmm.
Today we're zeroing in on a really fundamental shape in geometry, the triangle.
That's right. They're like the basic building blocks for so much.
Exactly. And our mission, looking at the material you shared, is to figure out, well, how do we know when two triangles are exactly the same?
It's this idea called congruency. And, proving congruency, it gives us a really powerful shortcut. Lets us compare shapes fast without measuring every little bit.
Yeah.
So yeah, we're going to pull out the essential tools, the key insights to make this super clear.
All right, let's dive in. Fundamentally, what is a triangle?
At its very core, it's the simplest closed shape you can make with straight lines. 3 sides, 3 corners, vertices, technically.
3 sides, 3 vertices, got it.
And it's rigid, that's important. Unlike, say, a square frame, which can wobble, a triangle holds its shape.
Rigidity. Okay, that makes sense. And there's a relationship, right, between the sides and the angles opposite them.
Absolutely. It's quite elegant, really. The material shows the longest side is always across from the largest angle. Always.
And vice versa.
And vice versa. And if 2 sides happen to be equal, well, then the angles opposite those sides are equal too. That's your isosceles triangle.
Right, isosceles.
And if all 3 sides match, then all 3 angles match 60 degrees each. Equilateral. It's like they're locked together.
Locked in. Okay. Now, the material also mentions some lines inside triangles. Medians, altitudes. Are these just fancy terms, or?
There's specific constructions. A median goes from a vertex, a corner, to the middle of the opposite side. All 3 meet at a point called the centroid.
Centroid. And that's?
Think of it as the triangle's balancing point. Like if you cut it out of cardboard, you could theoretically balance it right there on a pin.
Ah, cool. The balancing point. And altitudes.
Altitudes are different. They drop straight down from a vertex perpendicular to the opposite side. They meet at the orthocenter. Just, different ways to define key points inside.
Okay, interesting landmarks. Moving on to angles. The big rule everyone sort of remembers is they add up to 180 degrees, right?
Always. That's like geometry law number 1 for triangles. Non-negotiable.
Right.
And here's a neat trick the material mentions. If you extend one side out, that exterior angle it creates, its measure is exactly the same as the 2 opposite interior angles added together.
Oh, interesting. Okay.
Which leads to some useful facts, like a triangle can't have more than 1 right angle or more than 1 obtuse angle. It has to have at least 2 acute angles.
Right, because of the 180 limit.
Exactly. And crucially for congruency, if you know 2 angles, you automatically know the third because, 180.
But that ties it all together nicely. Okay, so let's get to the main event. Proving 2 triangles are identical. Congruency, what does that really mean?
Congruent just means perfect copies. Same shape and same size. If you could, pick one up, it would fit perfectly over the other one. No gaps, no overlap.
Perfect match. So all the corresponding parts must be equal too. Sides match up, angles match up.
Exactly. And this is where that acronym comes in handy. CPCTC.
Ah, yes. CPCTC. Sounds important.
It is. Corresponding parts of congruent triangles are congruent. It's like your geometric trump card.
Okay.
Once you've proven 2 triangles are congruent, using one of the shortcuts we'll talk about, CPCTC lets you immediately say any pair of matching sides or angles are equal. Without extra proof for that specific part, it's the big payoff.
The payoff. Okay, I like that. So what are these shortcuts? How do we avoid checking all 6 parts, 3 sides, 3 angles?
Right, we need efficiency. The material lays out 5 conditions, the minimum you need. First, SSS side, side, side.
Okay.
If you can show that all 3 sides of one triangle are equal in length to the 3 corresponding sides of another, they have to be congruent. Because of that rigidity we mentioned, fix the sides, you fix the angles.
Makes sense. It's next.
SAS, side angle side.
Side angle side.
Here, it's 2 sides and the angle between them. That angle has to be the one included or hugged by the 2 sides you're measuring. If those match up on both triangles, they're congruent.
The included angle, right. Got it.
Then there's ASA, angle, side angle.
Angle, side angle.
2 angles and the side between them. Again, the position of that side is key. It has to be the included side, connecting the vertices of the 2 angles you know. If they match, the triangles match.
Included side. Okay. Keep them coming.
All right. AAS. Angle, angle, cylinder.
Angle side. So the side isn't between the angles this time.
Correct. It's a non-included side. But remember, if you know 2 angles, you know the third one anyway, right?
Ah, because of the 180 rule.
Exactly. So AAS is basically ASA in disguise. You just need to make sure the side corresponds correctly. It has to be opposite an angle that matches in the other triangle.
Clever. Okay, one more.
Last one, special case. RHS, right angle hypotenuse side. This is only for right-angled triangles.
Only for right triangles, okay.
If you know the hypotenuse that's the long side opposite the right angle and one other corresponding side are equal in two right triangles, boom, they're congruent.
RHS. Got it. So those 5 are the gateways to proving congruency.
They are the rules. And one small but vital detail Material points out. Order matters when you write it down.
How so?
When you state that triangle ABC is congruent to triangle DEF, like delta ABC, delta DEF, the order ABC and DEF tells you exactly which parts correspond. A matches D, B matches E, C matches F, side AB matches DE, angle C matches angle F, and so on.
Ah, so the notation itself is a map for using CPC-TC later.
Precisely. It's your guide. The examples show this. You might use, say, RHS to prove two triangles are congruent. Then bam, CPC-TC lets you claim other corresponding angles or sides are equal because you've established the overall congruency. You use the rule to unlock everything else.
Okay, quick summary then. We've got the triangle basics, side link to angles, those internal points like the centroid, angle rules like the 180 sum and the exterior angle thing.
Yep. And then the big one. Congruent triangles, identical twins, and CPC-TC, the tool you get after you prove congruency.
Allowing you to state all corresponding parts are equal, and the keys to proving it are those 5 conditions. SSS, ANS, AS, AAS, and for right triangles, RHS.
Those are the shortcuts, the powerful rules that save you from measuring everything.
So thinking about these really precise rules, rules that guarantee 2 shapes are identical. Here's something to chew on. How does this very concept, congruency, governed by these simple geometric rules, actually show up all around us? Think about manufactured parts that have to fit perfectly, or the repeating patterns and structures even in nature. How much of our predictable world relies on these ideas of identical shapes?
It really makes you look at structures, both natural and man-made, a bit differently, doesn't it?
It really does.